Okay, let's talk about x-intercepts and behavior in 3.8, writing polynomial functions. This is going to be video part 2. So we're going to review the end behavior and x-intercepts using functions on the board, except we're doing this virtual, so we're not going to do it on the board. Let's talk about end behavior polynomials. Remember, end behavior talks about what's happening with the y values on the graph of a function as we go to the far left extreme of the domain and the far right extreme of the domain. So let's take a look at a couple of things on Desmos for us right now. Let's graph a couple of functions that have an odd degree. So let's do y equals, let's do x cubed. And now notice that the end behavior, as you go to the left, the end behavior, the y value, or the x value goes to negative infinity, the y values go to negative infinity. And as you go to the right, as x goes to positive infinity, the y values go up forever to positive infinity. So this is an odd degree polynomial, and the leading coefficient is just 1. So let's multiply this by 2, another positive number. So we see the positive leading coefficient didn't change the end behavior. Positive leading coefficient and odd degree still has, as x goes to negative infinity, y goes to negative infinity. As x goes to positive infinity, y goes to positive infinity. Let's change this to an x to the fifth, and let's add a few more terms in here. So plus 3x squared minus 2x plus 5. Oh, let's do minus 2. How about that? So now still we have an odd degree, 5, and a positive leading coefficient, and the end behavior did not change. Notice as the end behavior, as we go to the left, as x goes to negative infinity, the y's are still going down, so y goes to negative infinity. As we go to the right, as x goes to positive infinity, the y's are still going up, and y goes to infinity. So if we're describing the end behavior of this graph, then we would write that the end behavior of this graph as x goes to negative infinity, that's this direction, as x goes to negative infinity, y are going to negative infinity also. So when I write the end behavior, I write as x goes to negative infinity, y goes to negative infinity. And then I want to consider what happens on the right extreme. That's as x goes to positive infinity. Which direction are the y's going? Again, they're going up. So the y's are going to positive infinity. So we say as the end behavior, when I write this, I consider always x goes to negative infinity, x goes to positive infinity. Then I decide what my y's are doing in each of those directions. This is an odd degree positive leading coefficient, odd degree, positive leading coefficient. This is the end behavior and how we write that for the graph. So let's look back over here and let's make this a negative leading coefficient and see what happens. If I make it a negative, now look what happens. You change the graph for sure, but mainly what we're concerned with right now is the end behavior. And notice now that as x went to negative infinity to the left, y's are going up instead of down like they were before. We had a positive leading coefficient. So here as x goes to the right, or x goes to positive infinity, the y's are going down instead of where they were going up a minute ago. So the end behavior here, let's look at another one. Let's make this a cubic function instead of a fifth degree. There again, as x goes to the left, the y's are going up. So x goes to negative infinity, y's are going to positive infinity. As x goes to the right, y's are going down. So as x goes to positive infinity, y's are going to negative infinity. And if we just take a couple of these terms out, see if we can simplify this a little bit. Still the same leading coefficient, negative, an odd degree, gives us an end behavior where as x goes to negative infinity, y's are going to infinity. As x goes to positive infinity, y's are going to infinity, or negative infinity. So we take and pull this graph out. And if we want to write the end behavior, again, we consider as x goes to negative infinity. Well, let's see. Let's write that a little better than that. The y's are going up So we have y's go to infinity. And as the x's are going right, or x is going to infinity, the y's are going down, so the y's are going to negative infinity. So if we were asked to write the end behavior of this function based on odd degree and negative leading coefficient, we would say as x goes to negative infinity, y goes to infinity, and as x goes to infinity, y goes to negative infinity. And that would be the end behavior for an odd degree negative leading coefficient. Odd degree negative leading coefficient. So if we go back to, let's go back here, what we're looking at is if we have an odd degree and a positive leading coefficient, we would say as x goes to negative infinity, y goes to negative infinity, and as x goes to infinity, y goes to infinity. That's if we have a positive leading coefficient. If we have a negative leading coefficient, we would say as x goes to negative infinity, y goes to infinity, and as x goes to infinity, y goes to negative infinity. And that's how we would write the end behavior if we had an odd degree based on the leading coefficient, negative or positive. So now let's go and look and see what happens when we have an even degree. Let's go back to our graph. And let's change this to 4, since we got to know what a 2 looks like. Oh, that's interesting. Let's make this a little better than this. M2x, let's go ahead and first make this a +2 so that we can, oops, it's 22. All right, +2. Now, let's make it a little more interesting than this, and let's say that this is going to be minus, oops, 3x +4. Very interesting still. But let's look at the end behavior though. We have a negative leading coefficient and an even degree. And look at the end behavior. This time, notice when we had odd degree, the end behavior on the left and the right went in opposite directions. If the left side went up to infinity, the y's on the right side went down to negative infinity for odd degree. If we had the y's on the left went down for an odd degree, then the y's on the right went up to infinity on the odd degree. Now we have an even degree, and notice the end behaviors are going the same direction. As we go to the left, as x goes to negative infinity, the y's are going to negative infinity. As we go to the right, as x goes to infinity, y's are going to negative infinity. So the y values are going the same direction. Now let's look and see what happens when we make this leading coefficient positive, and it just flips it over so that now the leading coefficients, as x goes to negative infinity, y is going to infinity. As x goes to infinity, y's are going to infinity. So an even degree, the end behaviors go the same direction, either both up or both down. In an odd degree, then they go opposite directions. So one may go up while the other goes down. One does go up while the other goes down. The left goes up, the right goes down. As the right, left goes down, the right goes up. So here, if we go back to our little chart, whoops. If we're looking at an even degree with a negative leading coefficient, then that means they both go down. So as x goes to negative infinity, y goes to negative infinity. And as x goes to infinity, y also goes to negative infinity, because remember, even degree, they both go the same direction. The negative leading coefficient makes them both go down. If we had an even degree with a positive leading coefficient, like we just saw a minute ago, as x went to negative infinity, y would go to positive infinity. And as x went to infinity, y would also go to infinity, because they both go the same direction with an even degree. And that's how we do the end behavior based on the degree and the leading coefficient. Now, let's look at the x-intercepts and factors of polynomials. Let's think about a graph. And let's say that I have the graph of a polynomial function that intersects the x-axis at, let's say, -6, +1, and +4. Now, I told you before what we know about this polynomial, because we know that the y value is 0 when that graph intersects the x-axis. We know that if this polynomial is some function p of x, then p of x has a factor of x plus 6. So it means it can be written as x plus 6 times something, because if I plugged in -6 here, that would give me 0, and 0 times whatever this was is going to equal 0 and yield my y-intercept or my x-intercept there. But now, because I also know two other zeros, I can tell that there are factors there. If x equals 1 is a factor, or 0, an x-intercept, I know that x minus 1 is a factor. If x equals 4 is an x-intercept, then I know that x minus 4 is a factor also. So if we graph x plus 6 times x minus 1 times x minus 4, we should see a graph similar to this. Now, it may go up higher or down lower because we don't have any scale on the y-axis here. But if we go look at this, x plus 6 times x minus 1 times x minus 4, that was x plus 6 times x minus 1 x minus 4. If we zoom this out, like I said, it could be a lot higher or lower. We didn't know for sure. But you can see that it crosses at -6, at +1, and +4, just exactly like we showed you before. Definitely goes way higher because this is way up at 84 and this is way down at 120. But when we look at the graph, like I said, we didn't have any scale on ours, so we don't know how high that is or how low this is. But what I want you to see is the behavior of the graph, the x-intercepts, related to the factors. If you have any polynomial function that intersects the x-axis at known places, this one intersects at 0, I'm going to call this at A, and I'm going to call this at B. If A is a factor of the polynomial, if this is a function f of x, then we can say that f of x equals x minus A, because A is a factor, and then x minus 0, or that's just x if we do x minus 0, because 0 is an x-intercept. A was an x-intercept, so x minus A. 0 is an x-intercept, so x minus 0. And since B is an x-intercept, then x minus B has to be factors. Now, what we don't know is what makes that function taller or shorter, wider or taller or shorter. So there could be some constant multiplied out here other than 1. And that constant would also happen to be the leading coefficient. And that's what we're going to explore now. We're going to look at and identify functions based on their zeros, their x-intercepts. We're going to identify factors. And then if we can find another point that's not an x-intercept on the graph, then we can use that to find C. And that's what we're going to do here. The main thing you need to pull away from this video, though, is that if you have an x-intercept, if a graph of a polynomial crosses a function at the value x equals A, this means x minus A is a factor of that polynomial. And that's what you need to come away with this part 2 video.